let me start now. Thank you to be here. And let me open MATLAB. I think I upload in my study also the software, should be an M file in my study if you check. And then let me restart very quickly from the last sentence of last time. The reason to restart, to repeat is I receive feedback that the course is too difficult, not only from you, but also I receive in a couple mails. I mean, not difficult, but heavy, because in any case, for many students, it's a new language, even though for probably for um, data science students, it's a little bit boring. But anyway, I have to consider any all student in this sense, no? The mean value, no? The mean value. Okay, let me open MATLAB again, so we can. Okay, I found directly this version here. I hope that I click correctly. Yeah. Um, wrong. Okay. Was here, I am not able to find now. Ah, I think this. I am opening MATLAB, no? It's a shame here between zoom, between camera, between everything is really sometimes is also difficult to move among windows. Now I am opening also the lecture because I would like to recall some slide. MATLAB is nevertheless not open yet. In the meantime, let me share this to repeat a little bit what we did. I understand now. I opened 4 times MATLAB because the system didn't work, didn't respond. Oh, this is a little bit a problem now. Let me try to close some MATLABs because otherwise you have problems. I cannot. Okay, does not matter. This is the problem of to work with Zoom. Okay, last time we tried to apply in MATLAB. Do you remember directly this solution which we have at the end of the slide? Now we will open MATLAB. We will repeat shortly this concept, and we can see that here the solution is possible in analytic form of, let me say, yeah, considering just mathematical, just a mathematical expression, because I can, we have 2 reasons here. I can separate what I know with what I don't know. Do you remember the concept, what I know with what I don't know, as in high school? No? If you have the equation 2x equals 1, to calculate x, you have to divide by 2. X equals 1 divided 2. Because in this sense, we have the factor 2, which is somehow separated by the variable, and equal 1. 1 is what you know. Here is quite the concept is quite similar. Of course, if the equations, the equation is a little bit more complicated, which is not clear. It's not clear how to separate x with something which I know, for instance, exponential up to x plus sine of x equal 1. This equation is a little bit more complicated in order to explicit x as a function of something which I know. Here, please don't confuse now the notation. X is what I know in this case. Theta, if you look at the solution, what I don't know, I would like to calculate. But in any case, as I told you last time, here it's possible to write theta as a function of something which I know, x. I know x transposed, the transposition of a matrix. You remember what is the transposition of a matrix? Change column, interchange column and row. I don't know if you remember math. Inverse. If I say divided by 2 in gymnasium, no? 2x equal 1. To calculate x, I have to divide it by 2. The concept is quite similar. We have an inversion of something which I know. X in our notation is something which I know. It's the exploration matrix in which we have the exploration variables calculated at the exploration x point, no? X point. Y is the measurement, let me say in output. Is measurement in output. What do I measure if I put in a current equal what? 1 ampere, 2 amperes, and so on. Everything came from this representation, in which also here is clear the separation between what I know and what I don't know. Y, the vector Y, the measurements, it's what I know because are basically the output of my measurement. What is the meaning of the output? I put x equal 1, I will receive, I don't know here, 38. I put x equal 2, I will receive, I don't know, the value 3 or the 4, it doesn't matter what. This means this is no. The exploration matrix is no as long as I know n. The exercise which I did in MATLAB is an exercise in which n is fixed, is given. Today, we will see when n is not given. If n is a parameter to be optimized, a variable to be optimized, the problem is extremely complex. The reason is that I cannot separate what I know with what I don't know. Here inside this exploration matrix, I have x1, x2, xm, which I know, but n is unknown if n must be optimized. Theta is unknown, it must be calculated, but in these structures, as long as I have a structure in which I don't mix in the table, vector, table is matrix, of course, what I know with what I don't know, and as long as I consider a convex function, remember I told you about the convex function, considering your knowledge in the context of the high school. Remember this example which I did. If you have to optimize to find the minimum of a line doesn't have a minimum. Or if you have a minimum, it's minus infinite. But minus infinite, no meaning for us. The computer does not understand minus infinite. The computer does overflow. You remember this? I told you a little bit last time. No? The convex function to be optimized, extremely important also, this concept here. How I can choose the optimization function, we will see a little bit today. Until now, we consider this a least square. No? Therefore, the subtitle of this slide, or in general, what I am thinking, what I am presenting in this session of lectures is the least square, which is exactly this cost function, E transposed, the vector of the error, multiply, scalar, better to say, the vector of the error. The vector of the error transposed, scalar, the vector of the error, which is basically the Cn. Remember this in more explicit form, where is probably you know this cost function in this form. This is more natural one. Again, if you have these two conditions, we have a problem in this context here, which is a convex problem. With this solution, the unique solution which we have is this one. And let me now open MATLAB. Let me repeat a little bit again, two things, and then we will go ahead. I don't have much time, but I receive this indication that the course is too heavy. This means probably it's worthwhile to. I am a little bit ill. Let me close. Scusi. Want to stop a little bit. Excuse me again. I try to drink a little bit water. Let me. Ah, uh, it could be that I can go ahead. Sometimes, no. Second. Because the system didn't answer at the beginning and I opened for MATLAB. Yeah, now. Okay. Let me open the file. Where is? I'm looking for the file. I'm looking for the file. Um, hmm. Okay, let me see. Okay, I think this. Let me share. You remember this? Yeah. Very quickly, we have seen how we can build the structure of the data. Here, now I called with different name this vector here because students ask me if I can change the if I can use any kind of variable, no, that I call instead of y or instead of at the beginning. If you look at the lecture of last time, the lecture which I uploaded last time is phi. No, this is the flux. In the slide you have y. No? No? And then ask me, but I can put you put whatever you want. No? And is in a variable which you can call as you want. Do you remember? This is the data. In the lecture with y. Let me write y because power a little bit. But in your file you have a phi. The reason is don't fix the specific notation. This method can be applied in any kind of data set. This means it doesn't matter if we have a flux versus current, if you have a level of attention. Do you remember the example? The level of attention of students versus time, no? Because do you remember I told you could be represent this data could also represent this kind of phenomenon because we have a saturation. Sometimes I would like to say such kind of phenomenon, the level of attention over time is something which have a maximum because after some hour, for instance, in my case, I'm not able to think, I'm not able to be concentrated. This means the level of attention will decrease. Now, anyway, believe me, this data uh, could represent everything. No? Measurements. We have an exploration vector. Do you remember the concept? Row vector. Row vector. I call it here x, and you have the measurements y. The vector which typically is represented as in a column. No? This symbol here says that I transposed this row and this becomes in a column. But of course, it doesn't matter. You can put also here without transposition. You have to be careful in the rest of the program. Yeah, the solution is here. The solution is here, exactly what I told you now, exactly in the slide. Very important how we can build this matrix here. We have 15 measurements. You can consider here the measurement. Both vectors y and x consist of 15 values. Yeah, you remember the structure of this matrix here. I told you last time. We have the column vector x. Therefore, I put here, because here is represented in a row. This means with this transposition, I have in a column. This dot means each element of the column vector up to 5. Why up to 5 is fixed? Because I give you this at this moment. Don't care about it, because otherwise extremely complex, we will see together. Is the column, because if you look at the lecture again, the slide says, you can see that the colony characterized by x1, x2 until xm, each element up to n is in a column, x1, x2, of the exploration matrix up to n, each element up to n. And then I go, let me say, right, in which I consider the same column of the exploration variable or the measurements up to n minus 1 until up to 0, n minus n. And then I have a column of all 1. No? Every element up to 0 is 1. I don't know if you remember in high school. Therefore, here at the end, where is of this matrix, we have a column of 1s. This, if you look in MATLAB help 1s, you can see it's in a function with 2 arguments. The first argument represent the number of row. You can represent also matrices. No? Here represent the row, the number of row. Here represent the number of column. But I transposed. This means, what is the meaning here? We have a row with 15 column, with 15 element ones. And then I transpose, so that I have a column. The solution of our problem is already here, because we are looking for the parameters, which once I give the order of the polynomial. To calculate the polynomial means to calculate the parameter which characterize the polynomial. The solution is here. But of course, it's quite abstract, this solution, because if you want to visualize what happens, I have to produce the picture. I have to produce the plot. How we can do very quickly? I define another way a vector. This is also in a vector. It's in a vector starting from -5 to 5, as here, with cover the domain of the exploration variable. But what is the difference here? I am considering between -5 and 5 step with the amplitude 0,02. You can change also. The reason is I will consider a very long vector in order to represent in a pseudo-continuous form the the domain. If you look at I, let me run. If you look at I, this vector, again, at this moment, what I am doing, excuse me, I have to change everywhere, Paolo, no? Everywhere. Because it's a little bit strange. The question was if we can use whatever kind of uh, variable, and I put my name just to, yeah. Look, I see this new vector. 501 elements. Why that? Because I would like to plot the variable or the function in a pseudo-continue form. I will plot the variable, the polynomial in 501 points, and not only 15 points. Again, let me come back here. Once I define the domain, now I write a polynomial, which is we have the coefficient, in this case, A0, which multiply my domain, each element of the domain up to 5. We have A1, which multiply the variable of the domain, each element up to 4. No? As I told you at the beginning, A0 multiply x up to 5. This was the idea, plus A1, which multiply the domain x up to 4, and so on. Until AN, this one. We have a 6 parameter. Why that? Because we have the order of the polynomial equal 5. Then I plot, please help plot, phi C. Do you remember phi was the notation, original notation? You can write here, in the lecture, it was y hat in the lecture, but the y hat is strange too. Whatever, you can put whatever kind of notation, believe me. Grid is just to realize the grid in the picture. All don't maintain the same picture, because in the same picture, I would like to plot the original measurements, the measurements y versus x. Plot it using a star and a red star. This is an option of the command plot. If you look help plot, you can see the options which you have. At this moment, forget this line 28. The results, and then we will go ahead now with the lecture of today, is this one. The visualization of the results. The result is already in theta. Theta is a vector which compresses this function here in 6 values. This is the final sentence. If you want to see how it looks like the solution, the optimal solution in accordance with our constraints, polynomial or the phi, this must be done, must be given, must be, I have to say, so at this moment, this is fixed data, n equal phi y, we will see y. At this moment, it's fixed. I don't know if it's the best in accordance of my cost function. Again, the optimization problem depends, first of all, on the cost function. If I consider now we will see different cost function, we have a different solution, but not only. In this case, which I presented today, everything is depending on the order of the polynomial, and why the polynomial is also an assumption. Why not in a trigonometric function? Why not in an exponential function? Now, we will go ahead with the theory a little bit, and we will see how we can remove this hypothesis in order to have an optimization problem which does not consist of many constraints, or many hypotheses, or many assumptions. Or the assumptions should be, or must be, not so conservative. Conservative means not so strong. I mean, if I say optimize the polynomial order phi, we have 2 strong assumptions. First of all, the polynomial. Why that? I didn't clarify. I fixed. And why order 5? Now we try to remove this hypothesis. The critical point, which will remain, is the choice of the cost function. This is really something which depends of the problem, depends of our feeling. I don't want to say that is not scientific, but in any way, it's remain an open problem, because if I consider, we will see now another different cost function, we have a different solution. Typically, in optimization, then we try different cost functions, and then we validate through simulation, through measurement, what for us could represent a valid optimal solution. Let me go ahead now with the lecture, because it seems, if I remember well, that we concluded here last time, even though I think I already sketched. Look, SSE is exactly the cost function which we are considering until now, no? The least square. Do you remember? The sum of the error square, this means the sum of my measurements minus the point which I don't know, which I have to calculate through the coefficients, y I hat. This difference here, remember I told you at the beginning, is this different square plus this different square, and so on until this different square here. Now we can see this different square with different square in this context here with n equals 0, and here the different square is 0 because I am considering n equal 1 with 2 points. I will meet both. No? Just to repeat this. In some books, SSE means explain the sum of square. No? SSE. Is a deterministic error in the sense that yeah, we consider, let me say, deterministic elements, measurements, and yeah, approximations. In any case, it's defined as more deterministic than this one, because here we have the polynomial, which could be considered deterministic, of course, but the mean value of the measurement here could be improved writing mean value of the measurement, but it's clear. We cannot have calculated the mean, I mean, it's the mean value of the measurements. This means we have this element here, which is typical, it's the classical statistic, the most important statistic element of the data. This means this is called residual sum of squares and represented the statistical error because of the presence of this element, which is statistical one. This part here is extremely important because SST, total sum of squares, is basically, if you remember the PT statistics, the measurements minus their mean value, everything square, is the variance of my data set multiplied by my m minus 1. I mean, the definition of the variance is exactly SST divided m minus 1. Basically, is you can say, you can image is the proportional to the variation, to the variance. About that, I already told you that m, in order to work in this context, must be large enough. What is the minimum of largeness? Much larger than n, or better to say, much larger than n plus 1. I mean, if m equal n plus 1, I will meet all points. That we don't want to do that. Now, do you remember the idea? The idea, and then we will come back. We'll come back in a few minutes here. Why this approach is not suitable approach? Because we assume that the data, these two data represent really the process of the phenomenon. The points, the data, are affected by errors, that by noise, and by something which does not reflect the reality of the phenomenon. This means this kind of approximation, which is not an approximation, is typically not suitable. Much better this one. Much better this one. Even though, as I told you, this is a didactical example, because with 2 points, of course, at least in engineering fields, when we have a continuous variable, we have seen the flux over current is a continuous variable. It doesn't make sense to consider just two points. But in any case, theoretically, if I have 2 points, we have these two possibilities in order to analyze the difference between the deterministic approach and the statistical approach. I will come back here on a few minutes. Let me go ahead quickly. Yeah, here we can see a little bit a possible interpretation of this SSE, this SSE, which is again the difference between the measurement, the red color, and the black. Do you remember the difference between the measurement and its approximation? Yeah, just to flesh out SE. SSR is a difference between what yi at, you have just one point to be a little bit clear, and the mean value of all red. I mean, I am considering one y hat, and then I try to figure out again all together here this SSE, SSR, and SST, which seems to be the sum of both. But please pay attention. If you do mathematically this doesn't work. I have the demonstration. Work just if m is going to infinite. Because SSE plus SSR equal SST is valid if m is infinite large. But we consider nevertheless valid if m is large enough. We are engineering fields. We are not habit to work with infinite. I cannot put infinite value in the computer. This means, what is the meaning of infinite in our representation, in our conception? Means that m large enough, but or large enough means nothing for us. But if I say much larger than n plus 1, is an indication. What is the meaning much larger is, of course, remains a little bit not well defined. But of course, considering more and more number of measurements for a given n, and we can consider that SSE plus SSR almost equal SST. Here. Of course, in the case which we have here, doesn't make much sense, because we have 2 points, and n here is equal 0, and n is equal 1. This means here m is exactly equal n plus 1. Here a little bit better. But in any case, we cannot consider really, let me say, reliable this equation here. But let me didactically go ahead. Typically, we consider this valid, let me say, because m is relatively larger than n plus 1 to be precise, and we can write this expression here in this form. What I did here, I divided both parts by SST. We have 1 equals SSR divided SST. I divided both parts, by SST. We have here 1. We have here SSR divided SST, which I call R square, plus SSE divided SST. This means if SSR divided SST equals R square, if I rename, we can consider now this equation here, because we have R square equal 1 minus SSE divided SST. Now, R square is an indicator which came from this equation here, which we have to consider that is valid for m large enough, which can be used to evaluate somehow the approximation of our points with the model. Before discussing this and going ahead, here we have nevertheless a slide in which try to how possible to say to interpret a little bit SSE and at the end also SSR, which I defined exactly now. This SSE or least square is written here. This represents the statistical about the statistical deviation. We have a little bit to be clear what I intend of the response value, and I try to clarify it with respect to the model. And then in parentheses is written somehow it represents a deterministic error. It's a little bit statistical deviation, then deterministic error. It seems to be a little bit confused. That came from a book. A statistical deviation in the sense that this measured, in any case, the difference, this is correct, between the values and the model, of the point on the model. But of course, I consider the sum of the square. In this sense, we have a different distances with different yi. Somehow it's clear that is something nevertheless which can be considered and the distance between the point and the model in the sense of statistical meaning. We have a different distances for different y. But it's a deterministic parameter because we have the model and we have the measurements. We don't have directly any elements that characterize the statistic, like here. Yes, it's clear that is more statistical measurement because we have the difference between the mean value. In fact, here we can see that it represents the correlation between the response values in terms of a mean value and the predicted response value. The predicted this one. What is the meaning of the predicted? It's the model, because I can through the model I can calculate also element which I don't measure in the middle between two measurements or outside of the fields of the measurement. Outside a little bit more difficult. I mean, we have to be careful because we have a domain of the exploration matrix or explanation vector. But in any case, we have a prediction. We can say why I had is the prediction because it's the model. Because I can say what happens here, even though let me formulate, thanks to the model. Once I have the parameter, this means I can predict what happens between 3 and 4. It's clear what I intend. If I have the model, I can predict, I can calculate. But of course, the concept of this SSE, which represents somehow the statistic with respect to the model, and that we have this difference in the statistics in this sense here. Therefore, in the books, sometimes we find we find statistical so written, a particular statistic in this sense, but represent and deterministic error because it's the error of the model with respect to the measurements. Here is representing a correlation between the response values, again the model, but respect to the mean value. Therefore, he is properly the statistical error in this sense. Probably can help this sentence here. Value close to 0 of this SE indicates that the model had a smaller random error component. This is probably this sentence in the middle clarify a little bit better the concept. And that the fit will be more useful for prediction. Even though here we have to be careful a little bit, but close to 0, not 0, not in this sense. Let me now go ahead here. Now we can see from here that R squared is equal 1 in this case here. R squared equal 1 means exactly what I told you now. SSE equals 0. SSE equals 0. This means it seems that this model here could be useful for prediction, at least inside the domain between here and here. Outside we have to be careful because outside we don't have information. I mean, the domain always also here is any function is characterized by this value here, x1 on this axis, and x2 here. Do you remember in the example which I told you until now? No? But from -5 and 5 outside can be considered valid, but not far away from the domain. Not far away from the domain. That you have to be careful. But here inside, of course, this could be eventually suitable for prediction, for the reason which I told you exactly now. Because it's the deviation of the response with respect to the model. Here, R squared is 0 because we have this SSE is equal SST. Again, when I fit all points, SSE is equal 0. In this case, in which we consider the mean value as y hat, we have R squared equals 0 because SSE is equal SST. We can see from here. For instance, if yi, our model, equals y over line, this here, we have SSE equal SST. Therefore, we have R squared 0. Here we can see that we have R squared is always larger than 0 because it's SSR divided SST. Both SSR SST are squared. Look here again. This must be positive and cannot exceed 1. This means it's between 0 and 1. The minimum is 0 and the maximum is 1. Cannot exceed 1 because SSE cannot be less than 0. It's something square. We can demonstrate, this means, please pay attention, this means that R squared equals 0 is the minimum value, which I can have for R squared. And R squared equal 1 is the maximal one. But in accordance with what I told you about SSE, R squared equal 1 means SSE equals 0. This means here we have the minimal deterministic error, but the maximal stochastic one. Why that? Because this is given. If this is the minimum, this is the maximum. In this case here, R squared equals 0, we have exactly the contrary, because we have the maximal value of SSE, which is SST, cannot be more than SST, because if SSE is larger than SST, we have R squared negative. This cannot be. I don't know if it's clear. If SSE is larger than SST, we have thus S squared is negative. This cannot be, because SSR divided SST cannot be negative. This here means we have the maximal deterministic error, but the minimal statistic one, in order to understand a little bit this equation here. More in depth on this equation here, the data SST is characterized is the variance. The variance is the most important parameter or elements in a distribution, the basic, which summarize the characteristics, the statistic characteristic of the sequence. We can see for M large enough is equal SSR plus SAE. This means can be in this model, can be split into something which is oriented to the statistical error plus something which is oriented to the deterministic error. This means our original hypothesis, we thought at the beginning that the data are basically, or in general, a representation which came from data, or let me say the data are affected by a statistical error, and in the context of a possible model to represent them, a deterministic one. Now with this equation here, we can say that this philosophical concept to represent the data using a model which somehow summarizes the content of the data in terms of deterministic SSE and stochastic error is given. We can see that it seems to be consequent what I told you at the beginning philosophically of the course. Let me go ahead. Now, very important, R square is a parameter or an indicator. I don't have the demonstration, but we can see here, at least in one easy case, that with respect to the order of the polynomial is a monotonic function. I mean, we can see from here that n equals 0, r squared is equal 0. n equal 1, we have r squared equal 1. Of course, this case does not mean anything. The demonstration is a little bit more complicated, but we can see that starting here for this extremely easy example from 0 to 1, r squared is increasing. I can mathematically demonstrate, I will not do it, that is an monotonic function, r squared is a monotonic function with respect to n. This means it's not a good parameter or indicator to optimize n, because monotonic functions as indicators, as cost function, cannot be used in the sense we don't have an optimum of n. What is better, r equals 0 or r is equal 1? We cannot say because the r squared, with respect to n, r squared is not a convex function. Now, here is again something about r squared. Again, summarize what I told you before. R squared is defined between 0 and 1. I explained also why. And here, this sentence here is extremely interesting because we can understand that value close to 1, as is written, means SSE equals 0, do you remember? Or the close to 0, of course. In this case, equal. Indicating that a greater proportion of variance is accounted by the model. This is a little bit what I told you exactly now. Meaning, again, if I have 1, this means that SSE is equal 0. Did you agree? If R squared, this sentence here. Close to 1, this means SSE is equal to 0 exactly in this example. This situation here, in which basically the model is a close, no? Close to 1. Here, the model basically take 100% on the on the variation of the measurements. Okay, this is an example. Um, but what is the problem in this case? The problem in this case that we trusted, I told you at the beginning, totally the value, assuming that the value, the measurements, is the true. But we have the problem of overfitting. This is never acceptable in engineering. Now, let me conclude this, and then we open MATLAB to analyze an interesting problem, which is until now open. How we can choose optimal n? Choosing the optimal n means I can choose the optimal number of parameters. And then we can help also to choose the families of the regressor. Could be, we will see when I will will tell you about the trigonometric function. Look at this. If I modify it a little bit, the R square in this form here, it's an impossible modification. It's not the unique one. R square adjusted is the modification, an heuristic modification of R square, in which I multiply, I weight SSE divided SST. SSE, as I told you, is a portion of SST, no? Because SSE change from 0 to SST. When SSE is equal SST, we have the maximal value of R square. But again, SSE is also monotonic with respect to n. Therefore, R square is monotonic with respect to n. But if I multiply this SSE divided SST by m minus 1 divided m minus p, in which p is n plus 1, p is the number of the coefficients of the regressor of the function. What is the meaning? The meaning is, with this modification, R square adjust the resulting, let me say R square, which I called here R square adjusted, can be not monotonic, can be with some minima. Why that? Because increasing n, we can see that SSE will decrease. I told you, I didn't demonstrate, but intuitively I told you with this example, no? With 2 points. It's a stupid example, but we can understand well. But in the meantime, if SSE is decreasing, is nevertheless decreasing also the denominator, because increasing n, p will tend to m. Do you remember? M is larger than n plus 1. But if p is increasing, because it's increasing n, the denominator will tend to 0. This means we have the numerator which is tends to 0, and denominator in the same way. This means it could be that I can find a value of n, values of n, in which this R square adjusted is convex. This is a way to proceed very often is used, because nevertheless, we try to weight this parameter here, which nevertheless takes into account the variance of our approximation. Here is the explanation of what I told you. At the end, what we have, and then we will try to do an example with MATLAB. We have that if I try now to calculate the minimum of R square adjusted with respect to n, this is our goal. Because until now, I told you, yeah, that n is fixed. N is fixed. Now, assuming that n is not fixed, I would like to include in my optimization problem, so what is the best n? Why I put before n equals 5? This is the question. Because at this moment, I don't care about. Do the calculation with n equals 5. Now, this means that our problem we can reformulate in this form. We try to calculate the minimum of my R square adjusted, which I told you here. And here inside, I put R square adjusted. But in the meantime, let me say in this form, in the meantime, the parameter SSE divided SST is minimized with respect to theta. Let me express, let me clarify this formulation now. Until now, basically, until here, the problem was to calculate theta such that SSE is the minimum. Because remember, I told you that this is SSE divided 2, no? But divided 2 is a constant, it's not irrelevant in the optimization problem. It's there just for calculation reasons. Again, this is SSE divided 2, but the factor 2 is, let me say, is there historically. If you throw away the factor 2, is basically the solution is the same. The factor 2, because when I do the derivative, I didn't do here the calculation for you, I will cancel 2 with 2, no? Why that? Because until here, excuse me, until here, we are considering to minimize SSE. This means to minimize the deterministic error. To minimize the deterministic error for a given M. This means I can reformulate in this context the problem of minimizing the deterministic error and the stochastic one in this form, minimizing SSE with respect to theta. I will minimize the deterministic component of my R square adjusted, let me say, because we have this here inside, with the modification of R square, which came from the concept that the data are representable in the context of a model between considering a stochastic deterministic error. I can say in this form here. Minimizing SSE, I minimize the deterministic error. But to complete the problem in which I will include now the minimization of my Newton's function with respect to n, I will have basically the minimum of both, because R square or R square adjusted, if you consider this expression here, is related to SSR, to the stochastic error. Do you remember SSR is the stochastic error? This means minimizing R square adjusted with respect to n, I will minimize the stochastic component or the stochastic error of the data with respect to the model. Inside this problem, I minimize SSE, which represents the deterministic error with respect to theta. We split the problem in this form here. Therefore, we very often, yeah, we can say the equation 4 in which we consider a minimax problem in which we try to calculate the maximum of R square adjusted with respect to theta. We represent the minimum of SSE and the minimum of n. This means we minimize both the deterministic and the stochastic one. Okay, let me, do you have time? It's late, too late? Okay, if for you it's too late, we're fine. Um,
It's very important. Yes.
I would like to invest 10 minutes to show you MATLAB with an heuristic method. Why that? Because the problem is not convex. And this means we need solvers, which we will see in a couple of, in the next 2 weeks, I think. I will present one solver. The name is particle swarm optimization methods, which systematically can look for solutions in solutions, because we have more than one. We will see also today a little bit when the problem is not convex. Not convex means it could be. Let me come back here. That's this R square adjusted at more than one minimum with respect to n. What we are looking for typically, we will see now, for a solution for the minimal of a square adjusted with respect to n, but with the minimum n, because to have a big and a large, an higher order of a polynomial, an higher order of the model, can represent some drawbacks because of calculation load, to calculate many parameters, to implement inside a model and a function which approximate, I don't know, the inductance or the flux. If this is really complex, could be a problem in the context of a computer, or if you have a calculation load very heavy, if the calculation should run, in particular in the field of engineering, in microseconds, it's clear that one goal is to minimize the number of calculations. This means to minimize the n, to reduce the order of the model. Let me go in MATLAB. Let me give you, then we will repeat nevertheless this MATLAB part, which I introduced today, also next time. Optimization, let me see if I find now quickly. Um, hmm. I hope I share. Idea now, heuristically, this means not with the program, and we will do it. I will present at least one solver, which automatically look for possible minima when the problem is not convex. But let me intuitively show you what I do now. Heuristically, this means try and error. Look here. Very easy. We have exploration vector x, this one, organize in column form. We have a column because of this apostrophe. No? And we have a column of the measurement in output. Look, this is the regressor. Order of the regressor 1, n equal 1. I try to do at almost with n equals 0. It's easy, no? The mean value. But typically, the mean value, it's not the best one, believe me. Also, in this case, we will see it's not the best one, the n equal 1. Now we clarify what is the best one. Don't care about that. I will repeat starting from here also next week, no? Because this is important to understand. 1 second. Because I need to write something for you with the other camera. Again, I will try to do heuristically in order to show you the nature of the problem. Now, heuristically means by hands, trial and error.
Big pen.
I need a particular pen. A pen which I don't find now. Came from over here. Typically, I use this pencil because I make many mistakes, and with this I can cancel. I don't want to leave trace of my errors. Don't trust the professors who don't make mistakes. No? Everybody might make mistakes. The science is the history of mistakes. Uh, God don't want that we are perfect. God wants that we improve. Okay, a few minutes, really. I would like to sketch what I would like to look. This is exploration matrix. I don't need here to put transposed because I put here. You remember the concept of today again, I repeat it, the column, huh? The column. I don't need to put transposed. I don't need to put dot because I don't have up to, I have up to one. In this case, I don't need to put a dot. Again, why if I have a square, I need to put a dot? Because I have to define, because it's useful for me, I have to define what is the meaning of the vector square. Vector square, we don't have any possible definition. We define the vector square. We define as I put square all component of the vector. Now, here we have the theta. I copied exactly the solutions before. I told you I can define the domain. I have here again to visualize the solution. Remember, I told you a lot of today. I plot, uh, uh, let me say with this resolution, with this resolution between 0 and 30, because we can see that here we have between 1 and 29. Therefore, the domain here is defined between 0. I can write 1. And 29, theoretically, between 1 and 29. But I can include in the domain. And then grid as exactly as before, all done, and then I put also the values. Please pay attention here. Yeah, I have R square, and then after R square, yeah, next time I will dedicate, I put M, the number of measurements, I put N equal 1, exactly the order of the regressor. I put Pn plus 1, and I put R square adjusted. At this moment, believe me, next week I will go more in depth how I can define this, but basically I copy from the definition. Please pay attention, nevertheless, that here we have SSE. No? Yeah, we have SSE. SSE, excuse me, with the sum. And the denominator, we have SST. SST square. No, I have to include square too, excuse me. No. I will be more in detail next week. Let me run and let me show something very quickly. Then next week we will complete. R square adjusted is 0,977. R square adjusted. And R square is 0,9819. Results is this one. It's good, it's bad, we cannot say. We can say this is the optical result, and we can associate R square adjusted, which is our goal now, because we want to optimize with respect to n, with respect to theta. Which theta we have here? We have two thetas. Remember the name here. 1 second. Let me now consider a polynomial order 2. Try to do with the polynomial order 0 at home. Just one parameter to be calculated, the mean value. And then calculate, please, R square and R square adjusted. Let me the polynomial order 2. I am considering, of course, the same set of data. It's open. Why am I not able to open? Now. The set of data is the same, believe me. You can see. the polynomial is this one. This is the new exploration matrix in which we have each element of the column of the exploration variable squared. Then we have x as before, and then we have six ones. This is the solution. If you want, I can compare as before. No? I include just the x dot up to 2. Doesn't change the structure. Of course, yeah, to visualize, I need this one. But the solution now consists of 3 parameters. Now, look what happens on R squared adjusted in this case. Let me show. We can see that R squared adjusted decreases. Before was 0,98, now is 0,97. It's 1. 9.7. But R squared is increasing. Increasing n, R squared is increasing, and R squared adjusted is decreasing. Next week, we will go ahead. I will show you. Now, I can do that now quickly, and then next week we will go in depth. Let me consider. I mean, it seems to be both monotonic. One is increasing, as we know, R squared adjusted is decreasing. What happens for R squared considering a polynomial order 3? Why it isn't open? I don't understand. Yeah, now, very quickly. The data is the same. The polynomial consists of 3 parameters, order 3, 4 parameters. We can see from theta 0 until theta 3, 4 parameters. The calculation is exactly the same. Of course, I have to adapt everything on parameter, the 3 parameter polynomial order 3. Also, R squared, we will see next time in detail, and R squared adjusted. I have to update my value. We can see n equal 3. Look what happens. It's decreasing the square again. And this is increasing again. Let me see R squared up to 4 quickly. And then next week we will, it's here, we can see up to 4. Now look, this is the result, 9720, and before was 9631. R squared is always increasing. 9853, and now is 99. But R squared adjusted now is increasing because before was 96. This means n up to 3 is the first minimum which I find moving from n equal 1. You can try also from 0, n equal 0 is larger, not large. This means we can consider now, in accordance what I have seen, that n up to 3 for this example, it's didactical example, is a possible candidate. We will choose very often just this as the best because it's the minimum of n with the minimum value of n. I mean, it's the minimum calculated the minimum of n, because it could be that increasing n not very, the probability that we find is not so high, but in any case, it could be that increasing n, we will find an higher n with lower and lower square adjusted. But in any case, we have to pay the price that we have to include a lot of parameters. Typically, the first n which we find, the minimum n which we find, which you realize the minimum R square adjust is a possible candidate which we can use because nevertheless it's an optimal value with respect to R square. This means we minimize the statistical error with this n as the n is not so high. The deterministic error is nevertheless guaranteed, the minimum of the deterministic error is guaranteed by minimizing SSE. This means by this theta 1, theta 2, theta 0, theta 1, theta 2, and so on, theta 3 and theta 4 in our case because n is equal 3, by minimizing using the least square SSE. Next week, I will reconsider more in depth this example, so we can go in depth on the comments of the file which today I sketch. Now, of course, here's an heuristic way to proceed, to compare, to look. You know, we will see how we can use solvers to do automatically, you know, without checking and so on. To conclude, this method can be also useful to determine which kind of family is. Why that? Because n, in this case, is related to the coefficients. This means p is the coefficient. This means we will see, I think I will start next week, with the trigonometric function. The trigonometric functions, if you remember, are not characterized by the order, but characterized nevertheless by the Fourier coefficients, the number of frequency which I consider inside. Also, if you consider a sequence of exponential function, we have the parameter which define this exponential function. I mean, considering more and more exponential function with different arguments in the exponent, we have to calculate number of more and more number of parameters. This means we will see that we will optimize. Also today we optimize with respect to p because p is connected with the order in this case here. But p n plus 1 is the number of coefficients. This means to choose between trigonometric and polynomial, a criteria is the p. This means the number of coefficients. Increase the number of coefficients, we will look when we have the minimum for the minimum number of coefficients. Okay, let me close here. Thank you for your attention. If you have questions, I am here for you. Otherwise, we will see next week around past. No, and then now is the hour which it seems to be stable. This one. See you next week. Thank you for your attention.